My name is Zachary Gaudio. I am the project lead for the Design Build Fly project.
Hi, my name is Avery. I'm the aerodynamics sub-team lead.
Hi, I'm Carmina Sanchez. I am the propulsion systems lead.
Hi, I'm Lorraine Tilly and I'm the manufacturing lead.
Hey, I'm Sebastian Murdy. I'm the gliders, system, and deployment lead.
Hi, I'm Emma Serda, and I'm in charge of the electronics section for DBF 2025.
A little bit about Design Build Fly. It is a national competition hosted by the American Institute for Aeronautics and Astronautics, where every year a theme is chosen and an accompanying challenge and rules are published matching that theme. The theme of this year was the X-1 Supersonic Flight Program. The missions accompanying this theme consisted of a ground mission and 3 flight missions. The ground mission was a test to determine how quickly the aircraft payloads could be attached, said payloads consisting of fuel tanks and an autonomous glider. The first flight mission served as a airworthiness test where the aircraft had to navigate the course of flight with no payloads attached. The second mission, the aircraft had to have all payloads attached, where it would be gauged based off of how heavy its payloads were, as well as how quickly it navigated the flight course. The third flight mission, the aircraft had to safely deploy its autonomous glider from an altitude of 200 to 400 feet, and the glider had to land within a 200-foot square area. To undertake this project, we used a Gantt chart created using Gantt project to organize our team and as a continuously updated reference for all of the deadlines that we had to meet. To further carry this out, we divided our team into sub-teams to distribute tasks, and we would meet weekly to integrate our different subsystems as well as give status updates.
The 3 main manufacturing methods used for this project were foam cutting, laser cutting, and 3D printing. Wings for both the carrier aircraft and glider were originally foam cut. During our manufacturing process, we realized the foam cutter available for use could not accurately cut large tapered wings. This caused defects in the carrier aircraft wing, such as a disfigured leading edge. The glider wings are smaller and have no taper, so they could be accurately cut using the foam cutter. Therefore, the final glider wings were manufactured using this method. The empennage, wing box, control surfaces, and final carrier aircraft wing were manufactured using a laser cutter. We cut both balsa and plywood in a variety of thicknesses using this manufacturing method. The wing box anchor, nose, and body of the glider were 3D printed due to the geometric complexities of these parts. By 3D printing these parts, we were able to rapidly update our prototypes as feedback was acquired from testing.
All right, so next up is the aerodynamics and airframe development. We use laser-cutted balsa wood to build the airfoil spars that ran the length of the wing and the carbon fiber rods to connect them. We had 2 main carbon fiber rods in the rear that ran the length of the wing, and then 1 larger carbon fiber rod that connected the 2 motor mounts towards the front. We used 3 main 3D printed pieces that were split up into smaller sections to fit in the printer. You can see here the basic skeleton of the wing before we put the monocoat on it. Over here is the wing completed. Moving on to the wing hardpoints. So there's 3 main hardpoints. There's the motor mount, which we custom designed to attach the motor to the wing. Then on that same piece on the bottom side, we have the payload rail hardpoint. The payload rail would slide right in here, and it would be super easy on and off. And then next up, we have the wing box anchor. Looks like a platypus, but this is basically the spine of the plane. You can see right here, and it has these pieces that extend down into the wing box that would connect the wing box to the wing.
So for the electronics, 2 sets of different controls would be put on the carrier and the glider for final production. We use the FR Sky X8R receiver due to its support for S-Bus configurations. We use the Taranis QX7 transmitter, which came with 1 X8R receiver. And these are not very expensive. They're relatively cheap to buy. and then 2 sets of flight controllers were the Maytech Systems F405 Wing V2s. We used Avian 100 amp ESCs in conjunction with the motor mount and the attached motors. One direct port will be wired to the receiver, and then one servo connector will be connected to the receiver in a Y junction connected into channel 2 on our receiver. GPS will be wired with the corresponding ports into the flight control board. Some issues that we had is that some of the soldering was coming loose for some of the connections. And it's better to use pins in that situation. Also was the fact that sometimes testing indoors would not give the GPS a good receiver lock, and that kind of confused us for a second, but taking it outside gave us better results and actually gave us a GPS lock.
The two main challenges of Mission 3 are the deployment of the test vehicle as well as the design of the test vehicle itself. For its deployment, solenoids were selected as the actuators due to the simplicity of its movement. However, to ensure that the glider could dash statically and dynamically, the team built a test platform and used a vehicle to accelerate to the desired speed and at the release. During testing, it was clear that the tolerance between the glider and the solenoid piston allowed the test vehicle to wobble, so 3D printed brackets were installed to prevent this. Finally, due to the current requirements of the solenoids and the DC nature of these devices, the team opted for using a brushed ESC and a Trios battery to provide power. Now, the second biggest challenge of Mission 3 is, of course, the glider itself. Prototype 1 was focused on modularity and fast manufacturing, so a fully 3D printed plane was envisioned, but the tail control surfaces were too small and it proved to be laterally unstable. So, for Prototype 2, the control surface's size was increased as well as the dihedral angle, resulting in a more stable plane, but a plane that was also unable to pull up due to the small moment arm between the tail and the CG, as well as the overall overweight of the plane. It's worth to mention that Prototype 1 and 2 were tested using a octacopter that vertically released them. For Prototype 3, it was clear that a fully 3D printed plane was not viable, and the team came up with a 3D printed fuselage, longer foam wings, and a carbon fiber boom that connected to a balsa tail. This successfully improved the position of the CG, allowed for a considerably longer moment arm, and reduced the weight by 20%. Despite the fact that this prototype collided after being deployed, it was able to recover from a spin and a stall moments before the collision, which demonstrates the increased maneuverability and stability.
The challenge for the propulsion system was to get a 20-pound aircraft to go as fast as possible. For this, we used a Cobra motor with a kV of 850. It was paired with the 100 amp Avian ESC, which was all powered by the 4S battery of 6,000 milliamp hours, 14.8 volts, and a C rating of 50. To tie the whole system together, we look at the propeller performance data chart. Cobra Motor provides data charts where we can see potentially how the system will perform. The input voltage correlates to our battery of 14.8 volts. And we are below the recommended 60 amps, keeping us within the 100 amps of our Avian ESC. Here we see the static thrust test once both propellers have been attached. This is optimal to see how the whole system is performing.
you go.
Oh. It's in a stall. Nice. Nice. Oh, you covered it and then.